All right, so a couple review questions to start out with. This first one, a naturalist counts the number of baby birds or the clutch size in 130 different nests. The standard deviation of clutch sizes is closest to, so use the 95% rule that we talked about last time and see if you can estimate what you think the standard deviation is. And you can put your answer in the chat window when you get there. All right, good job. I'm pretty much seeing all the same answers over there in the chat window. So remember, the 95% rule says that if a distribution is bell-shaped symmetric, then 95% of the data will be within plus or minus 2 standard deviations. So in this case, this is a bell-shaped symmetric distribution. To use that rule to kind of estimate standard deviation, what we're going to do is we're going to cut off a little bit, 2.5% on either side, and then we're going to kind of draw lines where we cut that off. And in this case, they do tell us that there are 130 different nests. So if you have a hard time eyeballing what 2.5% is to cut off, then one thing that might be helpful is you can actually compute how many observations 2.5% is. So if I just take 130 and multiply that by 2.5%. Of course, when you do calculations with percentages, you do need to change them to decimal form first. So I would take 130 times 0.025 and, oh, hang on, I gotta grab my handy dandy calculator here. So I get 130 times 0.025, that gives me 3.25. So this just gives me a general idea of how much I'm cutting off on each side. It makes it a little easier sometimes, like I said, if you have a hard time guesstimating like what that 2.5% is. So this is about 3 observations on either side. And I can kind of tell how many observations I have by looking at the height of these bars. So my first bar here, I draw it over there. It looks like it might be 2 or 3. So that might be a good spot to cut off, is right after that bar. So I'm going to make my first cut there. And then same thing, this bar on the other side, looks like it might be 4-ish or 3 or 4. So I'm going to go ahead and just cut off that bar there. Okay, once I cut off my 2.5% on either side, I look at where my lines cross the x-axis. I'm going to take the big number minus the little number divided by 4. So my big number would be 11.5 minus my little number of 2.5, and then divide by 4. So that's 9/4, which is 2.25. So closest answer on there would be 2, which is what it looked like all you guys got. Okay. Here is another review problem. These are 19 scores that were on a driving test, and we want to look at this data. So the very first thing that we always want to do with our set of data is graph it. This is a quantitative variable, one quantitative variable. What would be a good graph to display the distribution of driving test scores? What do you think? All right, good. I'm seeing lots of votes for dot plot. And if I'm drawing a graph by hand, I think dot plot is definitely a good choice for that. So let's go ahead and draw a dot plot of this data. So to draw a dot plot, then first thing we have to do is set up our x-axis. So our x-axis just needs to be big enough that it's going to encompass the lowest and highest values. And you notice that I already put this data set in order for us from smallest to largest. Since there were so many numbers, just want to make it easy. So we need it to go from at least 5 up to 25 over on that side. Hang on my screen, all your lovely faces are covering up the biggest number, so just trying to move you over a little bit. Okay, so I've got my axis down here, and I'll start putting my tally marks. So I'll start at 1. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay, so 1, 2, 3, 4, 5, 6. And I'm counting by ones here, but you could set your tally marks up to be by fives or something like that too, and then put your dots in between, so that's not a problem. They just need to be like a ruler, so evenly spaced. Okay, so now I've got my axis all set up. I'm ready to go ahead and plot my points. So in a dot plot, remember, we're just going to put a dot to represent each of the observations here. If there's more than one value that's exactly the same, then we just stack those dots on top of each other. And in order to use this computer pen, I got to use an X instead of a dot because it does not like me to draw dots. So my first one was 5, then I had a 7, then there's a 10, then there's 15 and a 19. And then I have 2 21s, so I'll stack those on top of each other. Then I have 2 22s. Then I have 1, 2, 3, 4, 5 23s. So 1, 2, 3, 4, 5. And then 4 24s. And then I think I just have 125. Yeah, 125. Okay, so here's our distribution of scores on this driving test. And on a dot plot, or same thing if we were looking at a histogram, we're basically looking for 3 things, or you could think of it as 3.5 things if you use the SOX acronym. So what are the 3 things that we're looking for on a histogram or on a dot plot? Okay, good. Shape, center, and spread are the 3 things that we're looking for. So looking at this graph here, first let's talk about shape. Okay, so what shape do you think this dot plot has? Good, yeah, shape seems to be left skewed or skewed to the left, either way you want to say it. Okay, that's because the more extreme points, the long tail is over here on the left side. So that's where our skewness goes with. Okay, next we're going to look at center. And since we actually have the data points, then we don't really need to estimate it from the graph. We can just actually compute a measure of center. And we have 2 different measures of center that we've talked about in our class. What are the 2 measures of center that we've talked about? The mean and the median. So let's start with the mean. Now, do you think that these numbers here, these 19 test scores, do you think they represent a sample or a population? Yeah, I think they're a sample. I think there's a lot more than 19 people that have taken this driving test. So I think this represents a sample. So if I'm looking at the mean of a sample, what kind of notation would I use for the sample mean? Good, yeah, we're gonna use X bar as the notation for the sample mean. So remember, to calculate the sample mean, we're gonna add up all the values and divide by n. And what does n represent? N is what? Okay, the number of cases, yeah. Total number of observations, the number of cases. Since this is a sample, we often call n the sample size. So any of those things is good for what n is. So in this case, these were 19 scores. So 19 is going to be our n, and then now we have to add up all those numbers. So I'm going to get out my handy dandy calculator here and add those up. All right, so when I added them up, I got 378 for the total. And so if I take 378 divided by 19, then I end up with X bar equal to 19.89. So my sample mean, X bar, is 19.89. Okay, next we're going to find the median, and we'll go ahead and find the whole 5-number summary here. Before we find the median, just based on my graph here, would you expect that the median is going to be higher or lower than the mean? So just looking, knowing what I know about the shape of the distribution, do you think that the median is going to be higher or lower than the mean? Yeah, higher, okay? Because remember that the mean in a skew distribution is always pulled in the direction of the skew. So that means the X bar in this case is being pulled down by these outliers out there. And so the median, which will stay in the middle, is going to be higher than the mean. Okay, so let's look at finding that median here. So the median is the middle value. The first thing we would need to do is order the observations from smallest to largest. For this particular data set, then that's already been done for us. So they're already in order from smallest to largest. So now I just have to work my way over to the middle. And sometimes when there's a large number of data points like this, I mean 19's semi-large, I guess, it can be helpful instead of just kind of like taking your fingers and going outside, working your way in, and hoping you don't mess up anything in the middle there. There is a little formula we can use for the location of the median. So the location of the median can be found by taking n plus 1 over 2. So in this case, that would be 19 plus 1 divided by 2. So that'd be 20 over 2, which is 10. So what this means is that if I start counting from the left side and I count over 10 observations, the median is going to be my 10th observation. So this formula doesn't tell you the value of the median, it just tells you the location of the median. So if you find that helpful, you can use this. If not, you can just do what you've been doing normally. So I know that this is going to be, that the median is going to be my 10th observation from the left. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's my 10th observation. And if I counted from the other side, I should end up on the same number. So 1, 2, 3, 4, 5, 6, 7, whoops. Oh wait, I missed one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I do end up right here in the middle again. So 23 is my median. All right, so I'm going to write down the whole 5-number summary here. So we're going to have the minimum, Q1, the median, Q3, and the maximum. So now we've determined that the median is 23. So now I can go ahead and find the rest of the numbers in my 5-number summary here. So starting with the easy ones, let's find the minimum and the maximum. So what's the smallest number in my data set? 5, exactly. Okay, what's the largest number in my data set? 25. All right, so now I've done all the easiest ones. Now I got to hunker down and do the little bit more tricky ones. So I had an odd number of observations, 19, in my original data set. So when I'm sorting my observations, you know, you go here, you go there, you go here, you go there, then I'm going to be left with this one observation right in the middle. This is just like that one leftover Skittle. What do I do with the leftover Skittle? Yeah, I eat it, which means that it's not going to go with either side. If I have an odd number of observations, then the middle value does not go with either side. If I had an even number of observations, then all the observations would be in one side or the other because I could split those up fairly and all would be well. So if I had an even number, all observations would be in one side or the other. It's only when we have an odd number that we get to eat one of the Skittles. Okay, so Q1 then is going to be the median of this lower half of the data. And I think there's 9 observations here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the middle observation, if I work my way in from both sides, is going to be 19. I have 4 below and 4 above. So that's going to be my Q1. All right, and what about the upper side? So now I need to find the median of the upper half of the data here. So when I take the median of this side, what do you guys get for Q3? Okay, 24. So again, we're looking right in the middle here. That one. So there's 4 observations below, 4 above. So that one's going to be my Q3. So 24 is my Q3 value. Okay, so now I have my 5-number summary. What's the other measure of spread that we talked about? So we talked about 2 measures of center. It was the mean and the median. And then we talked about 2 measures of spread. One was the 5-number summary. What was the name of the other one? Okay, standard deviation is the other one. Z-score kind of goes along with standard deviation. It's kind of like a subset of standard deviation. So standard deviation is the actual measure of spread. that we looked at. So can I just go ahead and use that 95% rule to estimate standard deviation with this dot plot? So I'm assuming you don't want to use that nasty formula that we had. No, I can't use the 95% rule. I love the 95% rule. No, because it's not bell-shaped. Okay, so remember the 95% rule only works when we have bell-shaped symmetric distributions. And this one is not bell-shaped symmetric, so we're not going to be able to estimate standard deviation using that rule. So if we really wanted to know, excuse me, if we really wanted to know the value of the standard deviation, we would need to input these values into StatKey or Excel or something and have it compute it for us. All right, so looking at my dot plot here, how many of you think that this value 5, how many of you think 5 is an outlier? Would you consider 5 to be an outlier? You can just tell me yes or no. So is 5 an outlier? Okay, what about 7? Do you think 7 is an outlier? Wow, I'm getting a lot of no's. So a lot of people, you don't think 7 is an outlier? Some people saying yes. Okay, what about 10? 10 an outlier? Okay, mixed results still. What about 15? Is 15 an outlier? Okay, I'm getting mostly no's on that one. What about 19? You think 19 is an outlier? Oh yeah, everybody's saying no on that one. Okay, so we seem pretty clear. It seems like 19, not an outlier. Seems like we think 5 is probably an outlier out there. But a lot of mixed results for all these other values in here. So it can sometimes be really tricky to decide what's an outlier and what's not. Like how far does a point have to be away in order for us to call it an outlier? And so there's actually a rule, and it goes along with the 5-number summary that we can use to help us determine when we have an outlier. It kind of gives us that cutoff point where it says, hey, if you're below this or above this, you're an outlier. And if not, then we're not going to consider you an outlier. So it's a pretty handy way to detect outliers. All right, so this rule is called the 1.5 times IQR rule, or in Wiley Plus, like in your Wiley Plus homework, it's mostly just going to call it the IQR rule or the IQR method. Okay, but it's all the same thing. So 1.5 times IQR rule is the same as the IQR method or the IQR rule. They're just different ways to say the same thing. And basically what this rule says is that we're going to consider a data value to be an outlier if it is less than Q1 minus 1.5 times the IQR, or if it's greater than Q3 plus 1.5 times the IQR. So we're going to compute these quantities here, the Q1 minus 1.5 times IQR and Q3 plus 1.5 times IQR. And those are going to be like our determination points, basically. Okay, so values that are beyond those, that are more extreme than those, is what we're going to call outliers. So now I'm going to write those down up here, and we're going to try out this rule and see if we can figure out which values are actually outliers in that data set. All right, so first thing we need to do, this is the IQR rule, so we need to calculate the IQR. Remember that IQR stands for the interquartile range. So to calculate the IQR, then we take Q3 minus Q1. So in this case, my Q3 was 24 and my Q1 was 19. So 24 minus 19 is just 5. So my IQR is 5. All right, now remember our rule says we're going to consider something to be an outlier. So I'll write that down. So consider a point to be an outlier if it is, okay, and the first part says below Q1 minus 1.5 times the IQR. Okay, so now we can fill in those values. So Q1 was 19, and then we're going to subtract 1.5 times the IQR, which remember we just calculated the IQR to be 5. So I'm going to take 19 minus 1.5 times 5. And remember, when you're doing the calculations here, that you have to follow correct order of operations. So remember PEMDAS back from your algebra days or even just middle school math days. It tells us the order that we do things. So in this case, we're going to do this multiplication of the 1.5 times the 5 before we subtract that value from 19. And you have to be careful because sometimes people enter things into their calculator, and it just depends on some calculators will know what you meant and some won't know what you meant. Some will just do it like literally in the order that you put it in, and some will be like, oh, I'm going to follow order of operations. So so you have to be careful and make sure that your calculator is doing the order of operations correctly so you get right number out here. So if I take 1.5 times 5, that's 7.5. Then I'm going to take 19 minus 7.5, and I get 11.5. All right, so this means that if there are any values in my data set that are below 11.5, I'm going to consider those outliers. And we'll look back at our data set here in just a minute. Okay, let's also look at the other part of the rule, which says we're going to consider something an outlier if it is above Q3 plus 1.5 times the IQR. So for this data set, Q3 was 24 plus, then we'll have 1.5 times the IQR, which is 5. So remember, 1.5 times 5 was 7.5. So I'm going to take 24 plus 7.5, and I get 31.5. All right, so we're going to consider something an outlier if it is above 31.5. So below 11.5 and above 31.5. Okay, everybody with me so far? Okay, so I'm going to flip back up to where I had the actual data set, and we're going to look at these numbers here. Okay, how do we have any low outliers? Do we have any values that were less than 11.5? So these are my actual data values here. Are there any that are less than 11.5? Yes, yeah. How many do we have that are less than 11.5? 3, exactly. So values 5, 7, and 10, those are all going to be low outliers. Okay, based on our rule, we're identifying those as low outliers. So that means that that 15 is not an outlier, but these bottom 3 are outliers. Okay, now we're going to look at the high side. So on the high side, it had to be above 31.5. Do I have any observations in my data set that are above 31.5? Nope, I don't have any. So that means I don't have any high outliers in this data set. I just have low outliers. And that's, if you have skewed data, you're typically only going to have outliers on one side or the other. If you have outliers on both sides, then it's kind of a strange symmetric distribution that's like clustered in the middle, but with some outliers on both sides. So that can happen as well. But it's usually more of a symmetric distribution if there's outliers on both sides. Okay, so in our case, for this one, we decided we have 3 outliers at 5, 7, and 10. So I'm just going to write that here. So we have 3 low outliers at 5, 7, and 10. Well, I guess they're not really at there. These are the values of the 3 low outliers, 5, 7, and 10. All right. So it's kind of nice. It's kind of nice to have kind of a definitive rule. I mean, one of the reasons why I like math is because there's not all those little gray areas, like 2 plus 2 is always equal to 4, and it doesn't matter which math teacher you take or things like that, or if the math teacher likes you, whether or not she's going to mark that answer correct, which I feel like, I mean, and maybe I just feel this way because I'm more of a math person, but I feel like I took all these English classes and sometimes it was a little bit subjective, like, right? There's a lot of gray area. I don't like gray area. I like black and white. So I like this rule because it kind of gives us this black and white, like, you are an outlier, you are not an outlier kind of determination. All right. Something else that we can do with our 5-number summary is look at a graph called a box plot. Okay, so remember when we were talking about graphs for one quantitative variable, and we already mentioned 2 graphs for one quantitative variable that we talked about again today. So the first one was a dot plot that we already talked about. The second one was a histogram. And the third one is what we're going to talk about now, is a box plot. So this is another graph to add to our kind of toolbox for one quantitative variable. So this one's called a box plot. Okay, and basically a box plot is a graph of the 5-number summary. So it's a graphical look at the 5-number summary. When we draw our box plot, you can draw it either horizontally or vertically, and you'll see them both ways. All right, and here's what we're going to look for on the box plot, and then we'll talk about how to actually construct the box plot. Okay, so what are we looking for? Okay, well, first of all, we're going to be able to see where is the data concentrated. Okay, another thing that we're going to look for is whether or not the data is skewed or symmetric. So we're not going to be able to see the exact shape like we can with the dot plot or a histogram, but you can usually tell from the box plot whether the data is skewed or symmetric. So we can determine if data is skewed or symmetric. We're also going to be able to identify outliers using box plots, because on a box plot, an outlier is going to have a special symbol, so it's going to be obvious where the outliers are. So we're going to identify outliers. And another thing that box plots are going to be helpful for, like we said, it is a graphical look at the 5-number summary, so you can actually determine what the 5-number summary is just by looking at a box plot. So we can determine the 5. So if you just have a box plot and you don't have the data, you can figure out the 5-number summary by looking at the box plot. All right, I'll give you a second to write that down. Then on the next slide, I'm going to give you all the kind of step-by-step instructions for drawing a box plot, and I'll give you a second to write those down, and then we're going to actually construct the box plot, and you'll see how it works, and we'll talk about interpreting it. Okay, so I put in the chat window all the stuff that I have on this slide in case you're not quite done writing that down. And I'll switch over to the next slide so you can start writing down the instructions for drawing a box plot. And really, like, you'll write down these instructions, but then it all makes so much more sense once you're actually doing it. I feel like sometimes even the directions make it sound more complicated than it really is, but it's helpful to have the directions to step through the first couple of times that you're constructing a box plot on your own. All right, looks like most people are done writing. So now let's go ahead and see if we can construct a box plot for our driving test data that we've been looking at. So the first thing that we want to do is we want to construct our axis. And our axis is going to look pretty much like it would if we were going to do a dot plot, if you're doing a horizontal one. So we're going to do a horizontal one, but remember this could also be done vertically on a y-axis instead of on an x-axis. And kind of depending on the software that you use, you'll see them both ways. So I'm going to start by, like I said, drawing an axis down here. And this is a number line, so I'm going to set it up exactly like I did with my dot plot. So I'll start down here at 0, and I'm just going to put tick marks all the way up to at least 25. So, okay, so now I've got my number line all set up, got my tick marks, okay, and I'm going to write down the 5-number summary again just so we can remember it. Again, you probably have this all written down, and I keep changing slides though, so I keep having to refresh it. All right, so once we've got our axis, then the first thing we're going to do is we're going to create the box part of the box plot. And the box is going to go from Q1 up to Q3 with a line in the middle for the median. So what I do is I draw 3 lines, one for Q1, one for the median, one for Q3. So the first one, Q1, was 19. So here's 19 on my axis. I'm going to draw a line. Okay, then I'm going to draw another line at 23 for the median. So 21, 22, 23. Here's 23. So I'm going to draw another line here. Okay, then I'm going to draw a third line for the third quartile over here at 24. So there's my third line. Okay, then I connect all of these lines together and they form my box. So this is the box, part of the box plot. The box represents the middle 50% of the data. All right, once I have my box, and here I'll just label those parts that I put there. So this first line was Q1, the second line was the median, and the third line was Q3. All right, so now I'm going to draw a line that goes from my box to the smallest non-outlier point. So remember, we had some outliers, and we already figured those out, so I'll write those up here. So we had 3 outliers. Our outliers were at 5, 7, and 10. So let's go back up and look at the data set that we used here. There it is. Okay, looking at my data set, what's the smallest point that's not an outlier? So 5, 7, and 10 were outliers, but what's the smallest point? Yes, exactly, 15. So 15 was my smallest value in the data set that was not an outlier. So on my box plot, get back there. On my box plot, I am going to draw a line that goes from my box to 15, okay, because 15 was my smallest non-outlier point. So then I'll put an arrow there that just says smallest non-outlier point. All right, then on the upper side, I'm going to do the same thing. I'm going to draw a line from the box to my largest non-outlier point. Now, we already determined that we didn't have any high outliers, so that means that my largest non-outlier point is the same thing as the maximum. So if there's no outliers on that side, then you're really just drawing a line to the maximum, or same thing if it happened that way on the other side. So I'm going to draw, oh, whoops. I put too much pressure on the computer pen, then it thinks I'm trying to do something else. Okay, I'm just going to draw a line from the box up to 25. Okay, so this is my largest non-outlier point, which in this case is the same thing as the maximum. So largest non-outlier point. All right, now all that I have left is I'm going to identify my outliers by using a little asterisk for them. So following kind of the same plane as this line here, I'm going to put a little asterisk at 5. I'm going to put an asterisk at 7, and I'm going to put another asterisk at 10. So that identifies that those points were outliers based on our rule. And that's it. That's my box plot. Okay, and looking at this box plot, I can again see that the data is skewed to the left. I can tell that because I have all these outliers down here on this side. Also, you can see that the center line on my box is not right in the center of the box, but it's really squished close to one side. And these lines that extend from the box, they're called whiskers. I know it's kind of a weird name, but that's what they're called. But the whisker is a little bit longer here on the low side than it is on the top side. Also another indication that we have a skewed distribution. So by looking just at the box plot, I could tell that I do have a skewed distribution. And then, you know, I can identify the outliers, I can tell what their values are, and if I follow these lines down, if I didn't already know the 5-number summary, I could figure out what the 5-number summary was. So here's a couple more things to review box plots. Okay, so this is data that came from the winning number of hot dogs eaten by the winners of the hot dog eating contest from the years 2002 to 2015. So I don't know if any of you have ever watched the hot dog eating contest. It's actually, they usually broadcast it on ESPN. It's in July, like near the 4th of July, usually, that they have this contest every year. And it's kind of one of those things that if you're flipping through the channels and you happen upon it, like it's like a train wreck, like you can't look away because it's so fascinating watching these people just shove all these hot dogs into their mouth. So they have 10 minutes to eat as many hot dogs as they can. Okay, and this is the number of hot dogs eaten by the winners. Okay, so we're gonna answer a few questions about this. So first of all, what is the median for number of hot dogs eaten by the winners? So just using my box plot here, what is the median? Oh my gosh, I can see that we have some hot dog champion enthusiasts over in the chat window. Somebody actually knows the name of one of the really good ones. Okay, 60. Right, we can just follow that line over. Tells us that it's 60. Okay, next, a little bit tougher. Let's see if you can estimate the IQR. So using the box plot, see if you can estimate the IQR. Okay, so basically, remember the IQR is Q3 minus Q1. So I would follow this line over here. So it looks like Q3, the top of the box here, is going to be about 66. It's a little bit higher than 65. Now if I follow the bottom of the box over, then it looks like I get 54, a little bit lower than 55. So the IQR would be 66 minus 54, which is about 12. So 12 would be a good estimate there. Okay, what about an estimate for the range? All right, so same kind of deal in the range. The range is the maximum minus the minimum. So if we're following this over here, looks like it's probably maybe 68. I would say 68 or 69. So if you say it's 68, I don't know, I'm on the fence. I kind of think it might be 69. So either one, they're pretty close. And then if you follow this over, that looks like about 45. So you'd take 68 minus 45, which would give you 23, or if you called it 69, then you would get 24. So we can kind of estimate the range. Oh, thanks, Anna, for putting the math over there for me too. So yeah, so we can estimate the range on that. And we can see that the most number of hot dogs eaten in 10 minutes was either 68 or 69, which is a lot of hot dogs to be eaten in that amount of time. And the fascinating thing about this contest is like the people that are eating all these hot dogs, like one of like the more famous eaters, I guess, is this woman, and she's super teeny. She's like super petite, and yet she's like shoveling down all these hot dogs. They eat the bun separate and have this water that they try to put it down with. So I recommend watching it. It's kind of fun. All right, here's another question for you. Which of these box plots goes with the histogram of up here of waiting times for the bus? So this is what the histogram looks like. What do you think the corresponding box plot would look like? Do you think it'd look like A, B, or C? Okay, good. Everybody's choosing B, and B is the correct outliers. I mean, not the correct outliers. I read the word and said the thing at the same time. The correct answer. And one way we can tell is we can see that this is a skewed distribution. It's skewed to the right, and a skewed to the right distribution would have high outliers, which is what we're seeing here in our vertical box plot there. So nobody got confused by C, so good job. Okay, so next.
Can I ask a quick question about, so for the box plot in the box, can you tell based on where the median is in the box, whether the bigger side of the box or the smaller side of the box has more cases?
So
or
they
do you
have
tell
the exact same number of cases.
Oh yeah, okay.
So yeah,
It's
I
just
mean,
like,
it's
okay.
yeah, each part of, it's a good question though, because visually you're thinking, hey, you know, it doesn't seem like it's even split, but actually every portion of the box plot, so like on this one here, like there's 25% of the observations between that outlier and the top of the box.
Mm-hmm.
And then there's another 25% in this section of the box. And then in this little bitty section, there's another 25%. So that means that there was a whole bunch of people that had really similar values. And then this bottom part also has 25%.
Okay, thank you.
All right, so next we're gonna collect some class data here and see if we can analyze it, see what kind of distribution it has. So what we're gonna do is we're gonna see how long you can balance on the toes of one foot. So normally I do this in the classroom, and then you can have a buddy and your buddy can time you. So if you have a friend hanging around your house, definitely pull them over and see if they can help you out. But if not, you'll just have to kind of figure it out on your own. So if you have your phone, pretty much all phones have a stopwatch feature on them. So if you look for the clock and then you click on stopwatch, you can time yourself. If you don't have a phone, if you Google stopwatch, then Google has a stopwatch in there that you could also use. Okay, but how we're going to determine this is just like the picture of this super buff person that I found online. You want to stand on the toes of 1 foot, okay? So your timer is going to start as soon as you're up, and you stop your timer as soon as you put your heel down, you put your foot down, you touch a table, you fall over in any, and you get off your toes in any way, then that's when you're going to end your timer. Okay, and if you want to do like a practice run first, just to see how you're going to hold your balance, you can do a practice run first, and then do your real thing. And then I'm going to have everybody input our data, and we're going to check it out. Okay, so I'm going to put in the chat window, the place where you're going to enter it. If you're still holding on, don't let me ruin your concentration. Keep bouncing. I'm proud of you. Okay, so this next link, I just put it in the chat window. That's going to take you to the Google Docs. I'll show you what it looks like here. All right, and we're going to look at this data inside of StatKey. So when you've got the spreadsheet open, then find another browser window and open up StatKey, and we'll walk through together like how we're gonna analyze this. So open up StatKey somewhere, and once you've got StatKey open, then we're going to be looking at one quantitative variable. So open up StatKey, we're looking at one quantitative variable. All right, and this is obviously not a preloaded data set because we just created it. So we're gonna have to enter the data in ourselves. So to do that, we're gonna click on this Edit Data button here. Actually, before you click on Edit Data, let's go back to the spreadsheet itself. So go back to the spreadsheet. So I'm on the Google Docs spreadsheet, Google Sheet. There's probably no doc in there. Okay, and I am just going to highlight all the values in the time column. So I'm highlighting all the values in the time column, and then I'm going to right click and copy those, or however you copy things on your computer. I know there's not like a, I don't know, Macs kind of befuddle me, so I'm not sure what you click on to copy things in a Mac. But if you have a Mac, you probably know, so do that thing. All right, so now I've copied everything, all the values in the time column. I'm going to go back over here to StatKey. In StatKey, you want to click on where it says Edit Data. So we've already gone into that descriptive statistics for one quantitative variable. Now I'm going to click on Edit Data. I got to get rid of all that animal data that's in there. So you just highlight everything and hit Delete. And then I'm going to paste in, so Control V if you have a Windows computer. And that will paste in all the data that we just copied over from the Google Doc. All right, so once I've got this in here, the previous data set, the one with the animal longevity data, it said what animal it was and how long it lived. So it had an identifier column, meaning it had a column that identified what animal went with which observation. But our data set, if you just copied over the time column, does not have an identifier column. So you need to uncheck that box that says first column is an identifier. And then I did have a header row, like if you have time on the very first row of your data set, like I do, if you copied all that over as well, or if you put it in yourself, then you do have a header row, so you would leave that box checked. So if you got all that and you click on OK, then you should get a graph. If it gives you like improper format, then you probably forgot to uncheck the first column is identifier box. Okay, so go ahead and click on OK. Here's my data set. Hopefully yours looks like mine. The person that was super duper long at holding it, the 465, kind of snuck in there at the end. So depending on when you copied your data, you may or may not have missed that person over there. Okay, so here's my dot plot. Okay, and we can tell on this dot plot, like what kind of shape do you think this distribution has? You could also flip over to the histogram to see it as well. And you can click on the box plot. So what kind of shape does our distribution have? Skewed right, for sure. Like very, very skewed right. Something that's cool inside of StatKey, and you're probably going to find this helpful on the homework when they want you to identify the outliers, is that if I'm on this box plot screen, if you roll your cursor on top of those outliers, it will tell you the value of the outliers. So in our class, we had 2 outliers, the person who held it for 189 and the person who held it for 465 seconds. So those are our 2 outliers, so that's handy. Also on the dot plots, if you roll over the dots on the dot plot, it'll tell you the values of all of those observations. Over here on the right, to the right of the graph, we have all of our summary statistics. It gives us the mean, the standard deviation, the 5-number summary. So those are all great. Notice that the mean is 50.578 and the median is 23.5. So look at what a huge difference there is between the mean and the median because those outliers are really throwing off the mean. So for this data set, the median would definitely be a better indication for a typical value for this data set. So we can look at that. So anyway, that's how we're going to look at data inside of StatKey. Okay, so we've talked so far, we talked about 1 categorical variable, we talked about 2 categorical variables. We kind of filled out this chart earlier when we were looking at both of those. And now we've kind of finished with 1 quantitative variable here. And so let's kind of fill in this chart for 1 quantitative variable. So for 1 quantitative variable, what kind of graphs are going to be good for 1 quantitative variable? And hint, we talked about 3 different graphs now. Okay, so the 3 for quantitative variables are going to be a box plot, a dot plot, or a histogram. So I'll write that down here. So we have dot plot, a box plot, and a histogram. Okay, then when we think about numerical summaries for 1 quantitative variable, what kind of numerical summaries do we have for 1 quantitative variable? And we talked about several, so there's lots of right answers on this one. Maybe it'll help if you first think, okay, the IQR, yep, IQR is 1. Okay, the 5-number summary, standard deviation, good. Okay, those are a lot of the measures of spread that we talked about. What about some measures of, of center? I'll put standard deviation, 5-number summary. Okay, so yeah, we're gonna have the mean, and then the median is part of the 5-number summary, but we often list it separately because we look specifically at that so much. Okay, so these are all the basic numerical summaries that we talked about for range. We did talk about range, but typically we're going to use the IQR more than the range just because the IQR is resistant, where the range is not resistant. So when we're talking about notation for 1 quantitative variable, the only 2 things that we really talked specifically about notation for were the mean and the standard deviation. So we had X bar was for the mean and S was for the standard deviation when we were talking about samples. And then for populations, we used mu for the mean and we used sigma for the population standard deviation. The values in the 5-number summary don't really have specific notation that goes along with them, so that's why we don't mention those. But the mean and standard deviation definitely have specific notation. All right, so next we're going to talk about what to do when we have 1 categorical and 1 quantitative variable, which basically means that we're looking at a quantitative variable, but we're comparing several groups. And so essentially, because of that, everything that we do for 1 quantitative variable, we're just going to do it separately for each group when we look at 1 categorical and 1 quantitative variable together. So we can go ahead and fill in kind of the bottom part of this chart here, and then we'll look at an example. So, so for 1 quantitative variable, we look at dot plots, box plots, and histograms. When we have one categorical and one quantitative, we're going to look at stacked dot plots or stacked histograms or stacked dot plots or side by side. StatKey does everything stacked on top of each other, but some other software programs put them side by side. So I'm going to say stacked or side by side. Box plots, histograms, or dot plots. Okay, so all the same plots, but now we're going to stack them on top of each other because we're going to have multiple plots basically. Okay, when we're talking about numerical summaries, all the same numerical summaries that we did for one quantitative variable, we're going to do when we do one quantitative with one categorical, we're just going to do it separately for each group. So we're going to look at everything broken down by group. So I'm just going to say same as, I'm running out of room, I went on top of myself here. So same as one quantitative, but broken out by group. So I'll say but by group, that's shorter to say. So we're basically looking at all those. We're still looking at the means or 5-number summary. We're just going to look at them separately for each group. And in addition to that, we could also look at the difference in any of those variables. So I did not give myself enough space in this teeny tiny little box down here. It's also running into this other thing. So I'm going to write difference in means down here, kind of falling out of the box. So then notation wise, just like when we looked at two categorical variables, now that we're kind of comparing groups for more than one quantitative variable, we're going to use subscripts. So for notation, put x bar 1 minus x bar 2 and mu1 minus mu2. All right, so let's look at an example of this. Check over at everybody's pictures, see if how we're doing on getting things written down. It looks like you're mostly done writing. Okay, so here's an example. There was a study that they did at a restaurant in New Jersey where they wanted to see how what you wrote on the bill, if that could affect what kind of tip that you got. So it was an Italian restaurant, and before delivering the bill, the waitress basically randomly determined what message she was going to put on the bill. So a third of the bills got a message that said, "The weather is supposed to be really good tomorrow. I hope you enjoy the day." And another third of the bills got a message that said, "The weather is supposed to be not so good tomorrow. I hope you enjoy the day anyway." And then the third group got no message at all. So it was kind of like the control group. And what they measured was the tip percentage to see if one of these messages produced a different tip amount. So here's a question first. If the good weather tip percentages are significantly higher than the tip percentages when there's no message, then at the end of this study, could we conclude that the good weather message caused an increase in tip percentage? What do you think? Yes or no? Okay, good. So I'm seeing a whole bunch of yeses, and then I see yes because it's a randomized experiment, and that's exactly right. So this data is collected from an experiment, not from an observational study. So because it came from a randomized experiment, we can draw cause and effect conclusions at the end of it. All right, so yes, we can do that. So here's the different graphs that we created here. So here's the box plots for the 3 different groups. Good weather, bad weather, and no weather. And what we're looking for is we want to compare the shape, center, and spread for the different distributions. So basically that's what we're looking for. I'll write that up here. So we're going to, so on a regular box plot or histogram, we're looking for shape, center, and spread. When we have these stacked ones, we're just trying to compare the shape, center, and spread, comparing the socks basically. All right, so for example, on this one, If we look at the no weather, you can see that it looks like it's skewed to the left. We have a bunch of these low outliers here. If we look at the bad weather one, it looks a little bit symmetric-ish. We've got kind of outliers on both sides here. And good weather looks like it has a high outlier on the high side, so maybe it's a little bit skewed to the right a little bit. If we're comparing the centers, which one does it look like got better tips overall? Which condition? No weather, bad weather, or good weather? Which one looks like it got higher tips, a higher tip percentage? Yeah, it looks like the good weather message produced higher tips on average. So that's kind of comparing the centers. And then thinking about spread, which one of these looks like it has the largest IQR? No weather, bad weather, or good weather? Okay, so the good weather has the highest or the biggest IQR. Okay, which condition had the lowest individual tip percentage? So which one did we end up seeing the lowest value for tip percentage? The no weather, because we can see that that low outlier down there, that's the lowest tip percent that anybody got was part of the no weather. But if we're looking at on average, which one was lower, we can see that the bad weather is a little bit lower. So that's what we're looking for on there. We can also look for similar kind of things on the stacked histograms, which you see here. The nice thing about the histograms is that we can get a better indication of the shape here, looking at those. And we could also look at dot plots. So the dot plots and the histograms are a little bit similar looking to each other. This is what they look like inside of StatKey. I think StatKey kind of does wacky things with dot plots. They just always look a little squanchy to me, but they're still good. But I usually prefer the histograms, or when I'm comparing things, I think box plots are really great for comparing things. Okay, we can also look at the summary statistics. Here you can see that they're all broken out by groups. So we can compare the means, we could compare the medians across the group, and if we wanted to, we could calculate differences between any of the means. So this is looking at the difference in means for good weather versus no message. So we would just subtract basically 22.22 minus 18.73, and I get that 3.49. So that basically says that the good weather messages got an average of 3.49% higher tips than having no message at all. So I don't know how many of you are servers in a restaurant. Then you could go and apply this right now. If you're a server, do you write things on your bill? And do you feel like it gives you better tips when you do? And if not, and you want to collect some data, come talk to me. We could design an experiment and we could see if it actually help you. Okay, Brianna says it does help her get better tips if she writes something on the bill. But only write good things, like the bad weather message. Either the people thought that waitress was wacky for telling them there was bad weather, or they just didn't like hearing bad news, so they did not give her a better tip in that case. All right, so that pretty much sums up what you're going to do with one categorical, one quantitative, because it's essentially the same as one quantitative. We're just doing everything broken out by group, and then we can compare the groups. So I do have this fun video. Not that one. We didn't get to look at our data with the balancing on the toes. And I'll post this video that I was going to show you guys in Blackboard so you can watch it if you want. It's basically just how I used this information in chapter 2 to improve the cooking quality at my house. So if anybody has any questions, or if you want to go back and look at any slides, let me know. Otherwise, have a super fantastic weekend.